Hey there, and welcome. Sometimes in chemistry, the biggest answers don't come from some super fancy machine, but from something as simple as a little cloud forming in a test tube. Today, we're going to look at how chemists literally make the invisible visible using a really powerful technique. So think about this for a second. How in the world do you measure the exact amount of something when it's totally dissolved in a solution? I mean, you can't see it, you can't just pick it out. Well, chemists have this incredibly clever solution. You basically force it to appear out of thin air, or, well, out of the solution itself. And that is the magic behind precipitation titration.
All right, let's get into it. Here's what we've got on tap. We're going to start with the basics. What is this thing? Then we'll get into the key rule that makes it all work, the solubility product. We'll figure out exactly when a precipitate forms, what can mess with the results, and finally, we'll see it in action with a classic method called argentometry.
Okay, first up, what exactly is this technique? A lot of titrations you might know about look for a color change, right? But this one is looking for something you can actually see form right before your eyes. It's all right there in the name. In a precipitation titration, we're adding a solution we know everything about, that's our titrant, to the mystery solution we're trying to measure, our analyte. And the reaction between them, well, it doesn't just change color, it actually creates an insoluble solid. This sudden cloudiness, this precipitate, that's our signal. That's the moment we know we've hit the endpoint.
So how does the solution know when it's time to form that solid? Well, it all comes down to a really fundamental rule of chemistry, kind of like a maximum capacity that a solution just can't break.
And that limit is called the solubility product, or KSP for short. You can think of it as a strict, hard cap on how much stuff can be dissolved in a liquid. Every single salt has its own unique KSP value. Now, here's the key. If a substance has a really low KSP, it means the solution's capacity for it is tiny. It gets full really fast, which makes it much, much easier to hit that limit and form our solid precipitate. So the whole game really comes down to this battle, right? It's a showdown between what's actually floating around in the solution versus what the solution can possibly hold. And right at that tipping point, that's where we get our signal. To get this, we have to meet KSP's partner in crime, the ionic product, which we call Q. So if KSP is the absolute maximum amount of sugar your tea can hold before it just sinks to the bottom, Q is how much sugar you've actually stirred in so far. It's the real-time measurement of what's going on in your solution. And this table right here, it lays out the entire game plan. It's so simple. If Q is less than KSP, no problem. The solution is unsaturated and can hold more. If Q is exactly equal to KSP, it's perfectly saturated, you're right on the edge, but still no solid. But that one moment, the instant Q becomes greater than KSP, that's our tipping point. And this is the absolute key takeaway. You've got to push the solution past its breaking point. When the concentration of those ions, our Q, goes over the solution's maximum capacity, its KSP, the system just can't handle it anymore. The extra ions have literally nowhere else to go, so they crash out of the solution and form that visible solid precipitate. And boom, there's our signal. Now, this all sounds pretty straightforward, but, in the real world, chemists have to be super careful. There are a bunch of different factors that can totally mess with that delicate balance between Q and KSP. For instance, just heating up a solution usually increases its KSP, making it harder to get that precipitate. The solvent you use matters a ton too. Something might dissolve perfectly in water but crash out instantly in alcohol. Even the pH can shift the goalposts. And get this, sometimes if you add too much of your titrant, it can actually backfire and create a new soluble thing that makes your precipitate just disappear. So getting an accurate measurement is all about controlling these variables. Okay, so we've got the theory down. Now let's see how this all comes together in one of the most common and, honestly, classic methods of precipitation titration. Welcome to the world of argentometry. The name sounds fancy, but it just comes from argentum, which is Latin for silver. Why? Because the absolute star of this show is silver nitrate. This method is the gold standard, or I guess the silver standard, for measuring things like chloride, maybe in your tap water or in table salt. And what's really cool is that chemists have this whole toolkit for different situations. You've got the Mohr method, which is your direct, straightforward approach. Then there's the Volhard method, which is a bit trickier. It uses a back titration technique, which is perfect when the main reaction is kind of slow. And then there's the Fajan method, which is just super clever. It uses these special indicators that physically stick to the surface of the precipitate to signal, hey, we're done here. But here's the thing. No matter which of these methods you use, the goal is always the same. For this to work, you need that precipitate to form fast. It needs to be really insoluble, and that endpoint, that moment it appears, has to be super sharp and easy to see. So the next time you drink a clean glass of water, or take a medication that has a super precise dose, just think about this simple but powerful chemistry of making the invisible visible. This elegant technique is used every day to make sure our food is safe, our environment is clean, and our medicines work. It really makes you wonder, right? What other invisible things in our world are we measuring with such incredible clarity?